Hi guys, welcome back to the channel. Today we'll continue our discussion on threads. In the last video we have already seen how to create new threads using pthread create. We also saw how we can call pthread join in the main thread to wait for the other thread and not let the program exit. In this video we'll try to understand why it is important to join a thread, how we can set a thread in detached state, and then we'll move on to discussing thread synchronization using mutexes and condition variables. Let's get started. This is the pthread join function, which takes thread object as the first argument. Second argument is a double pointer that points to some memory location of a pointer in the caller. This address in the caller is used to retrieve the return value of the terminated thread. We should always make sure that the return value of a thread never lies onto the stack. This is also applicable for any function. We should never return something that lies onto the stack, because once the stack unwinds and this function returns, this memory region is available to be used for other tasks. For example, it could be used for setting up stack for a new thread function, and in such scenarios, our return value would get overwritten or corrupted. In most scenarios, the return value has to be on the heap. Pthread join API returns 0 on success and a positive error number on error. This is applicable for most of the pthread functions. They always return a positive error number in case of an error scenario, and 0 indicates a success. Pthread join function can be blocking in scenarios where this thread is already running and has not terminated. In such scenarios, pthread join would wait for the thread to terminate and then retrieve the return value of the terminated thread. In scenarios where this thread has already terminated, pthread join has a non-blocking behavior and it retrieves the return value immediately. It is important to note, if a thread is not joined, it produces a thread equivalent of zombie process. We have already seen what a zombie process is in our previous video. I'll add a link to that video somewhere on the screen so that you can understand what are zombie processes and how they get created. Zombie process can be understood as a dysfunctional entry that kernel has to maintain in its process table. This entry is needed because parent process would like to know what happened to the child, how child terminated. Did it error out or did it terminate successfully under normal circumstances? Kernel holds on to the return value of the terminated process in this dysfunctional entry, and it is responsibility of the parent process to clear this entry out by calling a wait system call. This is also called as reaping the child process. If we don't call pthread join on the thread that we created, it would lead to a similar scenario. In case of threads, kernel has to hold on to the return values to let other threads know what happened to the terminated thread. This value is held in a similar fashion in a data structure maintained by the kernel. And once we invoke pthread join on the terminated thread, this entry is cleared out and all the system resources are freed which were earlier holding this information. This scenario might also lead to memory leak in long-running processes that create multiple threads but forget to call pthread join on some of its terminated thread. Kernel will hold on to the return value of the terminated thread in such scenarios, and this would lead to memory being wasted away. We can prevent creation of thread zombies by making sure we invoke pthread join for all the threads that we create in our process. Or we can also rely on this approach where we set the thread to a detached state using pthread detach, where we pass the thread object identifier as the argument. Once we set a thread to detached state, kernel would automatically clean up this thread once it terminates. We can also use pthread self to get the thread object identifier to set the invoking thread in detached mode. This also returns 0 on success and a positive error number on error scenario like all other pthread functions. All the threads run within the same process, which means they have access to shared global variables in the data segment or memory regions inside the heap. But this sharing of data comes at a cost. There needs to be some kind of synchronization between thread that is writing the information and the thread that is reading the information. We must also take care that multiple threads do not attempt to modify the same variable at the same time. Otherwise, updates by few threads would get overwritten. To help you understand synchronization better, I have written a small thread function here which runs a loop and tries to update a global variable by taking a local copy on the stack, incrementing the local copy and writing it back to the global variable. Although I have not added pthread create APIs in the main, but let's assume we create two threads in the main function and each of the thread runs the thread function for 2000 times. Since both the threads try to update the global variable without any synchronization, there are chances that the output produced by this program is not correct. To understand this better, let's look at this diagram. Here we can see there are two threads running. Let's assume the first thread gets the CPU. It starts updating the global variable and does so till global variable reaches a value of 2000. At this point, it has taken a local copy of global, so the LOC variable would be 2000 at this point of time. Due to kernel scheduling, there are possibilities that the time slice for this thread expires and the thread 2 now begins execution. The thread 2 would read the global variable as 2000, update it repeatedly, and write it back. Let's assume it ran till a value of 3000 and its time slice also expired at this point. Now thread 1 would continue its execution from the point where it left. LOC, as we saw earlier, would be 2000. It would move on to incrementing LOC to 2001 and writing it back to the global variable. The global variable would now be 2001. With this, the increments done by thread 2 have been lost. Although thread 2 incremented the global variable till 2000, at this point when its time slice expired, its update were overwritten by thread 1 and the global variable went back to 2001. This is the consequence of accessing shared variables inside the loop without any synchronization. If a thread is accessing a global variable, another thread shouldn't be allowed access to that shared variable. Although it may seem if we replace these three statements with just the increment operator, it would work fine, but that is not the case. Even the simple increment operator is equivalent to these three statements on most of the architectures, which could lead to undeterministic behavior as explained in this diagram. To prevent multiple access to the shared variable, we have a notion of lock and unlock around the code section that tries to access the shared variables. Each thread before accessing shared variable would invoke the lock API and would invoke a unlock API before leaving the code where it accesses the shared variable. By this, if a thread is already executing LOC++, then thread 2 would not be able to enter this code section because it will not be able to acquire the lock as it has been already taken by T1. Once T1 exits this code section and invokes unlock, only at that point of time can T2 enter this code region. With this, the access to the shared variable is now protected. This can be done using mutexes. Fundamentally speaking, mutex is a variable that is used to protect the critical section of the code. It has the notion of locking a mutex and unlocking a mutex. The thread that has acquired the mutex lock is the only thread that can access the critical section of the code. We'll understand about mutex in detail in our upcoming videos.